Good morning, everyone. This is Dhruv Verma presenting our group with the topic Comparative Analysis of LRP and Lime on Audio Event Classification. So, moving ahead, I would like to introduce my teammates Pooja Gandhi, Jay Chotalia, and Krish Mehta. So, starting with the introduction, what is AEC? That is Audio Event Classification. So, anything that you hear or some kind of audio could be classified into some label. So, for example, I'm speaking right now, so that is speech. We add a label. If we have a dog barking, wow, wow, so that would be labeled as a dog barking. So, these are nothing but examples where we classify a particular audio into some label. So, here in our project, we are using XAI, which is explainable AI. So, for example, AI models are black box models. So, we don't exactly know how they work how they work inside or what is the process that leads to their decision. So, we use explainable AI models, which help us understand how a particular model would perform or what leads to its explanation that it classifies a particular label to an audio. So moving ahead, as I explained, we have audio event classification and explainable AI. Other related terms or keywords you would see further is feature extraction, where we select key patterns from audio data for analysis, spectrogram, which is a visual graph representation of a particular audio file. Apart from that, we are also using deep learning models, and there should be transparency in ensuring that AI decisions are clear and interpretable. Moving ahead,
Yeah, so hello everyone, this is Jay Chotalia. I would be explaining the problem with spectrogram. In most of the research papers that we came across, many were based on spectrogram conversion method. Now, in this spectrogram, there are two important components. One is magnitude and one is phase. Magnitude holds the most of the information of audio, whereas phase spectrum holds less information. Although it is like you can see phase is very random and it becomes a challenging task to accurately convert raw audio into spectrogram. Dhruv, can you please move on to the next slide? Yeah, so converting a raw audio file into spectrogram, there exists spectral loss, which is basically information loss, and we are calculating this by mean absolute error, which is a log function, and we'll get output from them. Next slide, please. Yeah, so you can see here that we calculated the information loss while converting it to spectrogram, which came around 0.18. So thus it becomes very important if we, correctly want to classify or predict raw audio labels without using spectrogram conversion method. Thank you.
just to display what exactly original phase and random phase are, I would like to play two or distinct audios. This was with original phase, and the next one is with random phase. Moving ahead.
Hello everyone, this is Pooja Gandhi. So here we go with here are some of the research papers that we went through. So can you just slides those research papers through? Okay, so after researching about the project background, what we found there are some of the gaps analysis from all of these previous research papers. Some of the gaps are What they do is they take the raw input file and they convert it to spectrogram, which results in loss of information. So we are solving this gap. We are filling this gap. Now the second gap is limited use of explainability. So in most of the research paper, we saw that they are taking the raw input file, they are converting into spectrogram, but there is a lack of explainability. They are not able to explain properly how the audio is classified or how the audio is detected further. Also, limited exploration of hybrid classification and also the limited research on the impact of background noise. So some of the gaps that we are able to fill in further our problem definition will explain. Okay, so here is the problem definition. So in traditional methods, in some of the research works, what we found out is they take the raw input file, they convert it to spectrogram. But because of this transformation, we see there is a huge loss of information. So our problem definition says that what we do is we work with raw audio files. Our input is the raw audio file. We retain all the informations and integrating it to the explainability to explain our classification. Some of the classification includes dog barking, clapping, fireworks, etc. Through next slide, please.
So coming to the objective, we aim to design and develop an explainable AI framework for our audio event classification, which directly processes the raw audio waveforms. So this, as we saw in previous slides, it enhances accuracy, provides robustness against background voice or noise, whatever we would like to call it. It provides more improved interpretability since we're using explainable AI techniques like LRP, and it can be used to solve real world challenges. And apart from that, this becomes a foundation for broadening applications which would be implemented in the future.
Okay, so here comes our proposed design. What we do is we first take the input as a raw audio file and then we proceed to a feature extraction which extract the features such as features, temporal frequencies, etc. Then we further do pooling, which will extract the more important features. Then we give these features, the important features extracted to the waveform CNN. So why we are taking waveform CNN is because waveform CNN is used to process the raw audio files. Uh, okay, so now waveform CNN has some full connected layers and predictions. And further, the waveform CNN will classify the output, such as dog barking, clapping, fireworks. And now we also put this raw audio file as an input to our LRP model, which is for our explainability. So it will explain our classification, and then we are merging our classification with our explainability as an output.
So going further, we realized that LRP was not that was not that explainability, the level of explainability that we expected. So we further moved down to this to compare it with line, which was traditionally used and it's still used. So this is the framework of that model. So we take the audio file, we load the audio file basically and convert it into spectrograph, as you could see. Then we use a random forest classifier. We train it on a particular data set and apply line. So line basically gives us explanations which are in the form of MFCC ranging from 2 to 13. It so all these MFCC classes they capture certain fixed characteristics or features of a particular audio based on the spectrograph, and it helps giving a local interpretation. So moving ahead, we created a permuted. So we took a sample and we overlaid that spectrograph with lime, as you could see, in this as a heat map form. Thus, it gives a output explanation that's for the line part.
Here comes the dataset details. So our total sample is 2000 audio recordings, which is further classified into five distinct categories. So our classes are 50 classes, which some of this includes like animals, natural soundscapes, human non-speech, interior sound, urban, etc. So we took this data set from the open source Kaggle. So further moving towards the understanding why we are taking waveform CNN over other CNN models. Drew, can you please? Yeah. So this is our comparison for the models. Why we are taking waveform CNN over other models. So here we can see that some of the models struggle with, for flexibility of the data set. Some of the models are limited towards generalizability. Some are more optimized for speech tasks. But we are taking waveform CNN because it is very generalized model. We can process the raw audio files. So, Drew, can you please go further? Okay. So this is the waveform CNN the advantages. So it is the most advantage of the waveform CNN is it is direct processing. So it is very simple pipeline which is avoiding the pre-processing step. It is directly processing the raw audio files, and it is also end-to-end learning. Like it learns the entire process from the audio to the classification. Also, it's some of the it also has a limitation, but we are not bound to it since our advantages are more stronger to work with our waveform CNN. Drew, can you please go for it?
Yeah.
Okay, so this is Krish Mehta, guys, and we thought of many XAI models that we could go forward with, but we figured out that why we should choose LRP over some other XAI models like Sharp, attention mechanism, based methods. It's because LRP is mainly focusing on giving visual representations of what's going on or what part of input is contributing to its output. For example, Sharp generally focuses on mathematics parts, but we over here we need some visual representation, so we go forward with LRP. Whereas attention mechanism just focuses on input region decision making and not the entire part. Whereas our LRP is focused on the whole process, the whole decision making process. Now, gradient based methods, it gives only importance to some parts of the gradients where changes happen, but LRP focuses on the whole process as mentioned above. So I'll like to say what is LRP and the mathematical part of the LRP through next speech. So what is LRP? It's LRP. LRP is a layer-wise relevance propagation, which is a technique that helps us understand why a specific neural network made a particular decision. For example, it tells us which part of the input, where most important part of the model's prediction happen. For example, if we have an audio of birds chirping in a audio data set, then it will help us figure out that which part of the audio or which timestamp of the audio actually the bird chirps at that time. So imagine you have a black box model like a deep neural network that makes prediction, but we don't know how it makes prediction. So LRP comes here, and LRP tries to explain the model's decision by showing which parts of the input were most responsible. So it's like, uh, first of all, we get the output from the waveform CNN, and then we figure out with the help of LRP that how it came. So it back propagates from the output to the input and gives relevance score to each input layer, each input neural network, and the highest LRP relevance score given to a specific neural network, that means that network has the highest contribution towards the output. So next go if we look at the formula part, Ri is equal to wij dot zj. Wij is the weight between the neural networks, and z is the neuron activation. And we have used epsilon in our formula to avoid division by zero. So our formula is basically on epsilon, LRP epsilon. So next page.
Yeah, so we have created or generated a simple use case in which we have merged multiple categories into a single audio, and we have classified it all. And we also give probability distributions of those individual categories. And yeah, so in the below figure, you can see there are three categories which were combined, which is clapping, dog barking, and fireworks. And there are probabilities of that also given there below. And on the right hand side, you can see individual relevance scores for those categories, which explains why did waveform CNN choose this category or labeled it in this category. Yeah.
So coming to the results part, as we framed earlier, that we had a particular raw waveform with LRP relevance overlaid on it in the form of visualizations. And at the contrary, we also had a spectrogram where line was applied. So the thing is that in our model, we focused on a global interpretable capacity, whereas line is only focused on local interpretability. So these two had different phases. I mean, they both have different meanings, but at the same time, when we were comparing LRP with like when we implemented LRP on many different labels, what we observed was that it was not visually possible to figure out if this particular raw audio file is of a bird chirping or a dog barking or person clapping, etc. Because even when we plotted the visualization of the relevance scores, there was very similar kind of relevance scores because major of them were greenish bluish in shade. So and majorly close to zero or 0.5. So it was very difficult for us to differentiate between the two. So we had to pivot to the point where we compared these two methodologies.
Okay, so as we come across the hypothesis, in this we have two factors on which we have tested our hypothesis. First is how the model performs on diverse datasets. So here we have taken two types of dataset. First is our own dataset, which is ESC50, and second is urban sound 8K dataset, in which all the sounds which are possible in the urban areas like dog barking and everything else is there. And in that dataset there are 10 types of different classes, and over 8,000 around labeled uh, audio. And so in diverse audio dataset testing, we have tested the accuracy, that how much accuracy waveform CNN and spectrogram. Spectrogram is for the showcasing the spectral loss which it causes, and waveform CNN directly converts the audio data into raw audio data, process directly raw audio data, and without any spectral loss. So we came to the conclusion that 88.2% and 86.5% is the accuracy given by waveform CNN, and as we can see, 86.2 and 85.8% is given by spectrogram, which is we can say that that's because of spectral loss. There's a gap between those, and so we have set an threshold for the this hypothesis of 85% accuracy. So as we can see, our model surpasses the 85%. Then thus we conclude that it is an alternate hypothesis. And next. So, second factor in this hypothesis we have chosen is robustness to noise. It means that how our model performs when there is some slight noise in the audio or some disturbance in the audio. So we have done this testing by calculating the F1 scores of both the models. As we saw that F1 scores are generally helpful when we are dealing with noises and variations. So for that we have set an F1 threshold of 0.75, and as you can see that waveform CNN easily exceeds that. Obviously spectrogram also exceeds that, but there's a there's a slight gap between waveform CNN and spectrogram. And while testing, we have used t-test over here, and as we got p-value less than 0.05, thus we conclude that alternate hypothesis is suitable for this part of the noise and variations. Next. So comparative analysis. Overall, we have seen everything. So first of all, we have noticed one thing. There is always two sides of a coin. So first, talking about the LRP part, uh, when using LRP, if we have two same temporal patterns audio, then we are noticing that LRP is not able to distinguish properly between those two audio sets, and while in other case Lime does it clearly. But also the con of Lime is that it produces some spectral loss, and thus both the side we have some pros and some cons. And whereas we have also seen that Lime is model agnostic, that which means that it can be applied on all the different classes properly. So I would like to go on to the conclusion part. So next page. So it's like I would like to conclude that we should use LRP if you want a faithful, detailed explanation of how your deep model processes raw audio without any spectral loss. And we should use Lime if you need some intuitive, high-level explanations, but are okay with some amount of spectral loss or information loss. So yeah, so our future scope will see if we can create both these models together, a hybrid one using Lime for interpretability and LRP for precision. And other future scope can also be uh, in crime detection and deep seek, in identifying the correct voices of someone, or to catch if someone is misusing someone else's voice. So yes.
That's the end of our presentation. Thank you.
Please like, share, and subscribe our YouTube channel. Yeah.
अरे भाई ऐसा इस पे नहीं जमता भाई बोलना बराबर, नहीं हो रहा था बराबर
नहीं
बोलना.
बनता भाई, obviously.